All right, so let's look at this very popular circuit, the voltage divider bias, that is used often for biasing the bipolar transistor in the forward active mode. And this circuit has to be contrasted with this fixed bias circuit here. And it solves some of the problems that are there with the fixed bias circuit. And if you look at the fixed bias circuit, basically what is happening is that one is fixing the value of IB here through this particular resistor here, RB here. So VCC minus VB by RB. So that fixes the value of IB. And then IC is derived from there. IC is equal to beta times IB here. And the problem with this particular circuit, as we all know, is that beta of the transistor can vary significantly, and therefore the IC will vary. And as a result of variation in IC, then the gain and the swing and many other properties will also change here. So this voltage divider bias with this emitter resistance RE solves the problem of beta sensitivity here. And it's easy to derive an expression like this here, that emitter current and collector current is almost equal to the emitter current here, is given by this particular relationship. And so the idea is that if we make RE much larger than RB by beta here, then what would happen is that the collector current would be practically independent of beta, and therefore it would be a stable quantity here. And one of the ways, the derivation of this particular equation is straightforward, but one of the ways in which this is explained, how the sensitivity to beta is decreases here, is through the operation of negative feedback here. So the idea is that this resistor RE that we put here, this resistor RE introduces negative feedback. And it's well known property of negative feedback, the word negative itself suggests that it will reduce the sensitivity. So for example, in this case, the sensitivity to beta is decreasing. So let's look at this particular operation of negative feedback in a little bit more detail and see where sometimes some things are not expressed in the right way here. So to look at the operation of negative feedback, let's look at this very popular book by Cedra Smith. And if you go to page number 448 here, the explanation of negative feedback in this voltage divider bias is being explained here. So let's look at all the steps that are, all the explanation that is given here in more detail here. So what it says is the following. So we have this voltage divider bias, and what it says is the following, that consider for some reason that the emitter current increases. So let's say the emitter current increases by a certain amount here, delta IE. Then it says that the voltage drop across RE, and hence VE will increase here. So there will be a change in delta VE. Right, so there will be a change here. So delta VE will also increase, right? So that's expected here. Now if the base voltage is determined primarily by the voltage divider R1, R2, which is the case if RB is small, it will remain constant. So what this in Cedra Smith is being said is VB is constant, or in other words, delta VB is 0. They are assuming it to be 0 here. So an increase in VE will cause a corresponding decrease in, because there is no change in delta VB. So there will be a change in delta VBE, which will be equal to minus delta VE. And so there's a change in delta VBE here. And then they say that this change in delta VB will reduce the collector current, and it will cause a change which is opposite to that originally assumed. All right, so let's write it down once more. Let's go over it. So step number 1 is that suppose delta IE increases for some. In this case, we are looking at the effect of beta. So let's say an increase in beta, let's say it increases delta IE. Then they say that as a result of which, so this is step number 1. Step number 2, the voltage drop across RE, and hence VE will increase. So delta VE will increase, will be equal to delta IE by times RE, right? That's step number 2. Then they say VB is constant, as we said, VB is constant, so delta VBE equal to minus delta VE, right? So that is there here. And this delta VBE will cause a change in current, and we know that change in current delta IC is equal to GM times delta VBE, right? So we can put here GM is IC by VT, and delta VBE is minus delta VE, so is equal to minus of delta IE RE, right? Minus delta IE times RE here. So what it says is the following, that there is a corresponding change here which is equal to IC RE times VT here minus the original change here, delta I. So there's a new change here, we can call it, because of the negative feedback. There's a change in collector current which is given by this term here, right? So that is what this particular explanation. So all the points 1, 2, 3, 4, 5 are exactly from the book, and this is what it is stating, that this is how the negative feedback is operating. There's a little bit of a problem here, and the problem is in point number 3 that we will see here. For example, it shows that the feedback current, the new current which opposes the original current, right, is proportional to IC times RE by VT times delta IE. Now this doesn't capture the way the negative feedback really operates, and in fact there's an error here, and the error is that VB is being assumed to be constant, and delta VB therefore is equal to 0. So let's look at that in a little bit more detail here. So we'll go through the same steps, but now with the following difference here. So the idea is that yes, delta IE will, an increase in delta IE, let's say, will cause a change in delta VE equal to delta IE times RE. That's fine. And we can call this as a small signal emitter voltage here. Now this small signal emitter voltage, we have built a small signal model here, the well-known small signal model of the circuit here, to look at changes, right? Small signal model of the circuit is given here. And so this is where the change in del VE is here. So as a result of the change in VE, there is going to be a change in VB, and there's going to be a change in VBE also. And for example, the change in VBE, we can calculate the change in VBE. What the VBE, the change here, the small signal VB, will be equal to minus, right, so let's look at some more space here. So will be equal to, the change VBE will be equal to minus VE, the original one, multiplied by R pi by RB plus R pi. All right, so this is what it will be. Now normally these circuits that we see here are designed in such a way that so that, for example, RB we often keep as much larger than R pi, so that we can get input resistance of a circuit like this is equal to R pi parallel of RB, and we would like to get input resistance as high as possible, so we like to make RB much larger than R pi here. So we'll assume that RB is much larger than R pi, so VBE equal to minus VE R pi by RB. So that's the change that we'll get here, right? And so that's the change here, VB is minus VB. And from here, we'll get a change in the collector current here. So collector current, there will be a change in collector current IC, or change IC will be equal to GM VBE, and that will be equal to GM is IC by VT, and we put VBE here. So let's put here, change will be negative. Change will be negative here, and let's put here the value. So R pi by RB and VE, which is equal to, that is a delta IE, RE times delta I, right? So this is the change that we are getting, and we know R pi equal to VT thermal voltage by IC times beta here, so we'll use that relationship. So we get a change in delta IC, which is equal to RE by RB by beta times delta I, right? So this is the expression that we obtain here. Let's circle this out here. All right. So it says that the feedback current here, let's call this delta IC dash here, feedback current is minus RE by RB by beta times delta IE here. And therefore, if you want the feedback to be strong, you would like to make RE much larger than RB by beta here, right? If you do that, then the feedback action will be strong, and the circuit will become insensitive to the beta, which is causing a change in increase in the emitter current. And this is also something that we see from this expression here, that the circuit becomes insensitive to beta only when RE is much larger than RB by beta here, right? This is the condition that we need to satisfy here, and this is what we get from this particular analysis. And note that the important point is we are saying that VB is not constant here. In fact, an offshoot of this is VB is equal to VE RB by R pi plus R beta, right? And we said RB is much larger than R pi, so VB is almost equal to VE here. So the change in VB, so in contrast to the previous explanation that you find in the book, where VB, change in VB is considered as 0, and therefore it gave us that the feedback current was IC RE by VT here, and it did not bring out the importance of the fact that RE has to be much larger than RB by beta here. And when you take into account this particular error here, and if you take into account the use a small signal model and you calculate the change in VBE here, then you get the proper feedback current, which is minus RE by RB by beta, and brings out the importance of that the feedback works strongly when RE emitter resistance is much larger than RB by beta here. All right, so as a summary, one can rephrase as to how the negative feedback works here. So suppose as a result of, let's say, increase in current gain of the transistor, the emitter current increases. That's point number 1. So that's suppose delta IE increases. The voltage drop across RE and hence VE will increase. That's point number 2. Increase in VE will cause a decrease in VB. That's point number 3. But this is where we make a change here. The delta VB that we calculate is different from when you make an assumption that there's no change in the base voltage here. And this in turn reduces the collector current, point number 4, a change which is opposite to the change that we get here in delta IC is opposite to the original change here. There's a negative sign here, right here, negative sign here. All right, so this is how, for example, the negative feedback works in reducing the sensitivity of the collector current to the current gain beta of the transistor here. All right, so let's stop here.